Hi, good day. In this video, we will be talking about an important equation when it comes to determining a certain population if they have differences when it comes to genetic manifestation. This is the Hardy-Weinberg Equilibrium Principle. The Hardy-Weinberg Equilibrium Principle made by Godfrey Hardy and William Weinberg states that a population's allele and genotype frequencies are constant unless there is some type of evolutionary force acting upon them. So what this tells us is that in a certain population, we can calculate the frequency of how a trait is manifested, be it homozygous dominant, homozygous recessive, or heterozygous. Now, for the Heidi-Weinberg equilibrium, we have some assumptions. And that is number one, there should be no selection or natural selection that should happen. We are not going to allow any environmental changes to alter the allele frequencies. Number two, there should be no mutation. So we are going to assume that no sudden changes within the alleles is going to happen within the generation of that genetic lineage. Number three, there should be no migration. So this means that we are going to assume that no two populations link together, since this can cause homogeneity among the populations and we do not want that to happen, di ba? Because it may alter the chances that a certain trait will be overshadowed by dominant ones. Okay? Number four, we should have a large population. So we need to have a large population since we are going to test the percentage of how a certain trait can be manifested. A small population won't give us any justice since as a small population percentage can change drastically over time. Okay, and lastly, random mating. Okay, we are going to assume that the trait that we are going to tackle came from a random mating since a trait from inbreeding, like for example, breeding of cows, something like that, in a farm, would give us a homogeneous result over time. Okay, so so if we are going to look at a certain population, say for example here on this illustration, the population of mustangs and the population of guppies. Guppies are fishes, okay? We cannot say that all the organisms in this population have the same genotypic and phenotypic manifestation. Of course, they're all different from each other. Therefore, what the Hardy-Weinberg principle is telling us is that the allele frequencies, the allele frequencies and the genotypic frequencies will remain constant given that all the restrictions and assumptions that I gave a while ago are followed. So, yun. Next. So, here's a simple visual example of what this principle is telling us. Say in a population of frogs, for example, this is a population of frogs. Um, some of the frogs may manifest a dark green color, this one. Okay? Some may manifest a light green color, this one. And some may appear to have a dark green, but is in fact a heterozygous allele combination, which is this one. Okay, so we are going to annotate the dominant allele, the dark green color with big letter G, and the recessive allele as small letter g. So additionally, we can also infer that the allele frequency, this one, the allele frequency, or the percentage of these traits appearing at a certain population. The dominant trait, which is the dark green, is around 0.6 here, or 60%. The light green, which is a recessive trait, would have 0.4 or 40% chance of appearing. And if you notice, if we are going to add these frequencies, the 0.6 and 0.4, they would add up to 100%. Okay. So now, we're going to derive the Hardy-Weinberg equation. So how did they come up, with this kind of equation? So in each chromosome, an allele can either be in its dominant form, which is letter P, or in its recessive form, which will be annotated as letter Q, okay? The probability of either having a P or Q is given in the equation 1 below, which is P plus Q is equal to 1. I'm so sorry. This is not a negative. This is just some sign to show that P plus Q is equals to 1. So why is this? Since like what I said earlier, with the big letter G and the small letter G here, they add up to 100% because they're the only alleles that we are going to consider. So even though the percentage of the big one, the percentage of this letter P and this percentage of this letter Q, whatever their frequency may be, they would always be equal to 100%. Ayan, okay? So next, to form a genotype by definition wherein it is the combination of alleles, two alleles must be combined. So basically mating, we have two parents and those traits, those alleles from those parents will be added. So if we're going to do that, we have P plus Q times P plus Q is equals to 1. So that will be our equation to combining them using FOIL method. We have P squared plus 2PQ plus Q squared is equals to 1, wherein the P squared is the homozygous dominant, the Q squared is the homozygous recessive, and the 2PQ is the heterozygous trait. So how did this happen? Kasi, if we're going to look at this, since we just did some math, P plus P times P is equals to P squared. Q times Q is equal to Q squared. And QP is 2QP. Diba? Since P squared and P squared, you add them up, PQ plus PQ, you add them up, that would be equal to 2QP. So these are the probability, no, that these traits will appear. Okay, no matter what the percentage of the dominant and the recessive alleles are. Okay, so since the equation 1 equates to 1, the equation is said to be a probability of a gene being homozygous dominant, yes, or recessive, or heterozygous, hence the name being genotype frequency of a given population. So later there is an example for us to see a visualization, a real example of how this works, okay? So given that there could be possibly more alleles are present in a genotype, the combination of multiple alleles must be done to compensate. Equation 3 below shows the general equation for the Hardy-Weinberg principle. Sometimes, there are certain alleles that manifest more than just two. Since, diba, for example, we just have two manifestations when it comes to a certain trait, two alleles, the dominant and the recessive. However, in some cases, um, however, it rarely happens to human beings. Sometimes it happen. Most of the time, it happens to fruits, no, to animals like amphibians and reptiles, something like that. Okay. So we're going to account those Ploid number. Okay. So for example, the Ploidy number is 3. So since there are three types of alleles that manifested in a person, so we're going to account that polyploid number as letter C. So here is a better visualization. This equation, this one. So P1 plus P2 plus Pn raised to C is equals to 1 raised to C. So that is the Hardy-Weinberg equation for a polyploid. Okay? So ayan. Next, here is the application. So for example, okay, letter P is the frequency of the dominant allele, okay? And Q is the frequency of the recessive allele. Now, using the Hardy-Weinberg equation, P squared would be equal to the frequency of the homozygous dominant. 2PQ is the frequency of the homozygous, and Q squared is the frequency of the homozygous, I'm so sorry, frequency of the heterozygous pala, yung 2PQ, and Q squared is the frequency of the homozygous recessive. Now, for example, the frequency of P or the dominant trait is 0.3 and the frequency of the recessive trait is 0.7. We are going to use the Hardy-Weinberg theory for that. Now, for example, for the homozygous dominant, so it's p squared. So 0.3 squared is equal to 0.09, which is 9%. And for the frequency of the heterozygous, which is 2pq, we have 2 times 0.3 times 0.7 is equal to 0.42 or 42%. And lastly, for the frequency of the homozygous recessive, we have q squared, which is equal to 0.7 squared is equal to 49%. Now, 9% of the 9% of the total population would be equal to homozygous dominant. 42% of the population would be heterozygous, and 49% of the population, okay, would be equal to homozygous recessive. If you're going to add that up, that would always be equal to 1. So that's what we're talking about. Na every allele manifestation would be always equal to 1. Okay? And here are some applications for 3 allele cases. For example, for human beings, probably the blood types A, B, and O. However, a certain person would only, di ba, would only account to A, B, or just O. Pero there are some cases kasi talaga na there are 3 allele cases. Okay, so that happens, the 3 allele cases. So what happens here is for the Hardy-Weinberg equation, we're going to have P plus Q plus R raised to 2. Ayan, so ganun. So in order to get the percentage of the for the Hardy-Weinberg equation, we can do the Punnett square, di ba? In order for us to determine the percentage of a certain trait, no, manifesting. However, that's basically no the point of the Hardy-Weinberg equation if we are going to look no for the similar traits or how a trait is being manifested in a population. So that's all. Thank you so much for watching and have a good day.